So welcome you back to this module. So last few lectures we discussed various approaches to compare estimators asymptotically. Asymptotically in the sense that as sample size becomes large or as n sample size n goes to infinity. And the two approaches which we studied were the limiting risk efficiency approach and then the limiting distribution approach. Now what we are going to do is in next few lectures we are going to study the asymptotic properties of some common estimators which we obtain using different methods of estimation. So if you recall your last course, two popular methods of estimation which you studied were method of moment estimators and maximum likelihood estimators. So in next few lectures we will discuss the asymptotic properties of these two kind of estimators. To begin with, let us first study the asymptotic properties of method of moment estimators. So that is what of method of moments estimators. Now you know what this method of estimation is. You try to look at how many parameters are there, then calculate those many population movements and then replace them with the sample movements, solve the simultaneous equations, and whatever solution you get, that gives you the method of moment estimators. So what you have is, suppose x1, x2, xn is a random sample with x1 having distribution function f, which belongs to the family P, which is a parametric family of distributions. So f theta such that theta is a k dimensional vector which is belonging to theta, where theta is a subset of Rk. So what I assume is the functional form of f theta is known. The only unknown thing is the parameters theta. So functional form is known. So I need to get k equations because I have to solve what are the solutions for theta 1, theta 2, theta k. So I need to get k equations. So the minimal set of condition which I need is that the k moments of f exists, or in other words, I define, suppose for every theta mk or mr theta, which is expected value of x1 to power r, for r is equal to 1 to k, exists. So what you do, these are the k population movements, so they were k parameters, so I found out k population movements. I equate them with the k sample movements. So I define equivalently ARX as a RS sample movement. So 1 by n, summation I is equal to 1 to n, xi to power r is equal to 1 to k. So these are, as you know, are called population movements. These are called sample movements. So method of moment estimator, which you in short call as MME estimator. Let me denote that by theta hat, which is basically theta 1 hat, theta k hat, is the solution of simultaneous equations MR theta hat same as ARX. So you replace population movements by sample movements, solve for theta 1, theta 2, theta k, and whatever you get, that is the method of movement estimator. Now, if theta hat is MME of theta, and suppose h is a function from theta to lambda, which is a subset of Rm, then I called h theta hat as the MME of h theta. Is called the MME, method of moment estimator of h theta. So in particular, if this function is just taking the ith ith component, h of theta 1, theta 2, theta k is theta I, then it says that theta I hat would be the MLE of the ith component, which is theta I. So in particular, if theta hat is the MLE of theta, theta I hat x is the MME of theta I. Now let's see some of the comments about method of movement estimators. Now note that method of movement estimators relies on the fact that the first k movement exists. So if the movement does not exist for the distribution, the method of movement estimator cannot be used. So the method of movement estimator do not exist or method of movement estimator procedure is not applicable when one or more MR theta do not exist. So simplest example could be Cauchy distribution. Cauchy distribution, even first movement does not exist. So I cannot talk about estimating theta in the Cauchy distribution because the movement does not exist. Any movement doesn't exist. Example, Cauchy distribution. So this is one major drawback of method of movement estimator, that it assumes that the movements exist. Remember that that is not the case with the maximum likelihood estimator. Maximum likelihood estimator does not assume that movements exist. It only assumes that the given likelihood equation which you get has a solution. Now there is a possibility that even if movement exists, these simultaneous equations which you are putting over here does not have a solution, or it does not have a unique solution. The MME may not exist when simultaneous equations let me call this as simultaneous equations 1 do not possess a solution. Now there is a possibility that when you are equating MR theta is equal to ARX, there is a possibility that certain movement does not depend on theta. Then what you are saying is you get an absurd thing. You are saying that RS sample moment is same as some fixed quantity independent of theta. So for example, that is the case if you're talking about normal 0 sigma square. If you take the first moment, expect x1 is equal to 0. And if you try to use method of moment estimator, it said 0 is equal to x bar. Equating first moment is equal to sample mean, and second moment is sigma square is 1 upon n summation xi square. So the first one doesn't give you anything, 0 is equal to x bar. So in those situations, one can use the modified MME method by ignoring those equations where MR theta does not depend on theta. And then you consider some additional equations so that, and you go until the stage when you get a unique solution. So in situations where MR theta, one or more MR theta, do not depend on theta, the MME may not exist. So in such situations, one may ignore such equations such population movements and add additional population movements and equate them with corresponding sample movements. So idea is simple. There is a possibility that, for example, if you look at the normal 0 theta case. So what is the first population movement? It is the mean, which is 0. What is the first sample movement? X bar. So it says you should have 0 is equal to x bar. But that will not give you anything. So here the method of movement does not exist because there was one parameter, so you will consider only one movement, which is the first movement. First population movement is 0, first sample movement is x bar, so 0 is equal to x bar does not give you solution for theta. So method of movement estimator here fails. So what this remark is suggesting is, in such situations, one can go to the higher level of movements, or one can have additional population movements and can equate them with sample movements. So I go in the normal 0 theta case to the second movement because the first one is not giving me anything. So second thing is, second population movement is theta, which is variance. So I replace theta hat is equal to second sample movement, which is 1 upon n summation xi square. So theta hat is equal to 1 upon n summation xi square turns out to be estimator. So this is called, when you use such a method, it's called modified method of moment estimator. Now, another is, even if this equation has a solution, it may have more than one solutions. So MME may not be unique. So these all properties you might have studied in your last course as equation 1 may not have the unique solution. Now note that what you are doing over here is replacing ARX, which are sample movements, with the corresponding population movements. So first thing you should note is 1 upon n summation xi to power r. What is its expected value? Its expected value is mr theta. So ARX by weak law of large numbers is consistent for mr theta because it is the average of xirs, and xirs are IID. And what is the expected value of each xir? It is mr theta because they are IID. So that means by weak law of large number, this sample mean of xirs will go to the population mean of xirs, and population mean of xir is nothing but mr theta. So what you get is AR is a consistent estimator for mr theta. So A1, A2, AR is a consistent estimator for M1 theta, M2 theta, and MK theta. So let me add that remark over here. So E A1x, A2x, and AKX is consistent for M1 theta, what is a movement estimator? Movement estimator says you solve that. That means you will be looking at an inverse equation. So that means if this transformation is continuous, and of course Jacobian of transformation is non-zero, which would say that this is a unique solution. If that happens, then I can say that method of movement estimator is consistent because you get method of movement estimators of theta by inverting these equations. So if M1 theta, MK theta are continuous functions of theta, which will ensure that their inverse transformations are continuous functions of theta. So this, when you invert this and get the theta in terms of A1, A2, AK, that would be a continuous function of theta. And I know that this is consistent for this. Inverse image is also continuous. So convergence in probability is preserved under continuous transformations. So this would ensure that theta hat is consistent for theta hat is consistent for theta. And the Jacobian which is del M1 theta, MK theta determinant of this is non-zero, which ensures that the transformation is 1, 1 or the solution is unique. Then the MME theta hat is consistent. So this is a very nice property of a method of movement estimator, that it has the desirable property that theta hat is consistent for theta under quite general conditions. What it assumes is that this transformation which you get from mr theta to A1k, theta to M1 theta, M2 theta, MK theta, that should be continuous and 1, 1, in the sense that Jacobian is non-zero, then theta hat, method of movement estimator, is consistent for theta. So in particular, if your function h from theta to lambda, which is a subset of Rm, is continuous, then the MME h theta hat is consistent for h theta. Now note that this A1, A2, AKX are sample means of IID components. The A1 is sample mean of xi's, A2 is sample mean of xi square, sample mean of xi cube is A3, and so on. And you know that vector of sample means always by central limit theorem have a asymptotic normal distribution. So what you know is A1x, A2x, AKX after suitable normalization. Of course, centering has to be done with, because A1x has a mean m1 theta, A2x has a mean m2 theta. So centering has to be done with respect to m1 theta, m2 theta, mk theta. And then root n is a normalizing or a scaling factor. So root n, A1x, A2x, AKX as a vector minus m1 theta, m2 theta, mk theta would go in distribution to normal 0 sigma star. So you have asymptotic normality. So if delta method is applicable, if the multivariate delta method is applicable, you can say that the distribution of theta hat also after normalization would have asymptotic normal distribution, provided H is smooth enough. You know that for delta method to be applicable, the partial derivatives would be continuous and so on. So from this, I also get that method of moment estimators would be consistent and asymptotically normal. We have root n times A1x, A2x, AKX, which are sample means. So it is a vector of sample means. These are sample mean of xi's, these are sample mean of xi to the power k, minus the corresponding means mk theta. Root n is the normalizing factor. By central limit theorem, you know that this goes in distribution to normal k, 0, sigma star for some so under assumptions of D of f, of course, which assumes that these partial derivative exists, transformation is 1, 1. What you will have? You can apply the delta method, H inverse of that, so that means root n. When you apply the inverse of this, you get theta hat. You apply here, you get theta, m inverse theta. So m inverse of this, m inverse of theta goes in distribution to not nk 0 sigma for some. Just applying the delta method, because you know that if root n x bar minus mu goes to normal 0 sigma, then root n h x bar minus h mu goes in distribution to the Hessian matrix of h mu times normal 0 sigma. So that is what it is happening over here. Okay, so what is the h you are applying over here? Because you want to get a theta, so you are trying to apply m inverse of that. M1 inverse, M2 inverse, Mk inverse. So when you apply this M1 inverse, Mk to Mk inverse, that is what the inverting through equation, through those simultaneous equation is happening. So here you will get a theta hat. So method of moment estimators are consistent as well as asymptotically normal. So what we saw is a method of moment estimators which has an intuitive appeal, is consistent under certain conditions, under quite general conditions. In fact, what you need is that transformation is such that m1 theta, m2 theta, mk theta, such that the transformation is 1, 1. Partial derivatives exist, they are continuous, Jacobian is non-zero, then your method of moment estimators would always be consistent and asymptotically normal. Of course, you might have seen in your last lecture, last course, that method of movement estimator has another big disadvantage, that it may not depend on sufficient statistic. Or sorry, it may not depend on a minimal sufficient statistic. So let me write down this as another remark. And another drawback, method of movement estimator may not depend on minimal sufficient statistic. So that means if your loss function is convex, you can always improve in certain situations the method of movement estimator. Now we'll see a few examples of that kind in the next module. So these are some basic properties of method of movement estimators, and what we see is some of the properties are encouraging in the sense that they have the most desirable property, that your estimators should be consistent. So we found that they are consistent under quite general conditions. They are also, the convergence rate is quite reasonable, which is 1 upon root n. Asymptotic, so they are can also, consistent and asymptotically now. So with this, I would stop discussion about method of movement estimators. What I'll do in the next module is, I'll consider some examples and would show that how does this theory which we talked about here holds in those particular examples. So that's all for this module. See you in the next module. Thank you very much.